morning. The purpose of Chapter 3 is to lay the foundation for everything we're going to do in inferential statistics, which is the second part of our course. So we kind of fly through probability, and I want you to realize that you're just skimming the surface of a huge topic. So in 3.1, we see several basic concepts brought to our attention that you may or may not already be familiar with. So I'm just going to run through the definitions. In my opinion, I would print this and try to fill it in first and then listen to me explain. But if you're feeling lazy, follow along. So here we go. Definitions needed. A probability experiment is an action or a trial through which specific results are obtained. An outcome is the result of a single trial in a probability experiment. The sample space is the set of all possible outcomes of a probability experiment, and an event is a subset of that sample space. A tree diagram is used to give a visual display of the outcomes of an experiment. And we'll look at one in a minute. A simple event is exactly that, simple. There's only one outcome. The complement to an event is everything, so the complement to event E is the set of all outcomes in the sample space that are not included in event E. And it's often denoted with E prime. Some books use EC for complement. Some even use E bar, which is awful because that's kind of like a mean. Our textbook uses E prime. Okay, so I asked some questions ahead of time for you guys to go and fill out, but let's look at them together. So if I roll a die as my experiment, what are the possible outcomes? So the sample space would be that I either rolled a 1, a 2, a 3, a 4, a 5, or a 6. Question 2 says if I roll a die and want the outcome to be an even number, then my event is to roll an even. And you have to ask yourself, is this simple or not? Because that affects how we'll create probabilities. And so the event is what? If I got a 2, a 4, or a 6, and that's not just one outcome, so it's not simple. And it's that simple. Haha. Okay, draw a tree diagram to represent tossing a coin twice. I'm going to do that over here off to the side. So a tree diagram starts with, well, what are your possible outcomes? So you're doing what? Tossing a coin twice. So when I toss the coin, I either get a head or a tail. Then after I've gotten a head and I toss the coin again, I would either get a head or a tail. But if I had gotten a tail on the first try, then I could have gotten a head or a tail. What it allows us to do is follow the branches, and a branch, there's one branch, there's another branch, here's another one, and here's another one. The branches give us our sample space. So our sample space would be that you could get a head, a head, tail, a tail head, or a tail tail. Now, the tree diagram is probably more useful if there's more than two things going on, but anyway, that's an idea of what a tree diagram does. All right, number 4 says use the fundamental counting principle, and nowhere in here have we talked about what the fundamental counting principle is. So the fundamental counting principle can be found in your book. You might want to look that up. But it does this. It takes everything into consideration and just multiplies it all together to figure out how many different combinations you can make. So we want to do license plates that consist of one letter and 5 digits, and the digits cannot be repeated. So I'm going to do it as a fill in the blank problem. I need one letter and then 5 digits. 1, 2, 3, 4, 5. The fundamental counting principle says you're going to figure out how all of those things can happen and multiply them all together, and that'll tell you the number of different combinations you can have. So we ask ourselves, how many letters are in the alphabet? Well, there's 26 to choose from. Yeah, yes. How many digits are there? Well, there's 10, 0 through 9. But it says they can't be repeated. So once I've picked a digit, then I only have 9 to pick here, 8, 7, and 6. And so I can multiply all those numbers together and get the total number of ways that you can create a license plate. Now we have 780,240 different ways to create license plates. Now that's not really how a license plate is done, but we'll get over it. All right, list the 3 types of probability and give an example of each. So what are the 3 types of probabilities? Let me insert some space here so I can write. All right, so I have classical, I have empirical, and I also have subjective. Now the classical is the theory-based. Empirical, you collected data. And subjective is like an educated guess. That's what I'm going to write down, an educated guess. So like the doctor will tell you, you have a 30% chance that this growth is going to like reform or whatever. He doesn't really know that. That's just an educated guess based on either research that he's read or maybe some personal experience with his former patients. Okay, so if I take into account rolling the die, if I wanted the probability of rolling a 6, well, the probability of rolling a 6 is that I would have 1 chance out of 6, all right? But what if I have you roll a die? So pause the video, roll a die 5 times, write it down. So I'm going to do that. Okay, so I repeated the experiment 10 times. I rolled a die 10 times, and here's what I got. How many 6s did I get? Zilch. So my empirical probability of rolling a 6 was a 0. Okay? Whoa! All right, that was loads of fun. Let's see, what else are we supposed to talk about? I asked for you to draw the scale that's on page 137 with the range of values for the probability of E. Probability of E being the probability of an event happening. So what's the smallest probability you can have? You can actually have a probability of 0. That's not what I want to write. I want to write that the probability of the event is 0. And you can have the probability of the event being 1. That's the lowest value, that's the highest value. Halfway in between would be a half. I'm smart like that. And what do these mean? Well, if it's 0, then we're talking about it's not possible at all, like at all, okay? Like 0 chance that you're going out on a date this Friday. None. All right. And if the probability is 1, that's 100% certain. That's a sure thing. So we say what? This is a certain to happen. Not possible and certain. What's right in the middle? Even Steven. And then somewhere in here is unlikely. And somewhere in here is probable, or we'll use the word likely. Okay? So if I tell you the probability of an event is 0.2, might take it with a grain of salt, right? Okay. All right. Our last question we were to ask ourselves was, if you know the probability of an event is 72%, what's the probability of its complement? So number 7 says the probability of an event is 0.72. The probability of its complement is everything else. So 100% spans the whole scenario. So we do 1 minus 0.72, and we find out that the probability of the complement is 0.28. That should get us through 3.1. I mean, it's pretty much just vocabulary. 3.2 and 3.3 are basic rules. And so I'm going to come back with a separate video for that.